Why does this droplet create a massive splash while this one barely makes a ripple? The answer involves invisible air layers, molecular forces, and physics so complex that scientists are still trying to understand it.
What's up, guys? Today we are diving deep into one of the most fascinating physics phenomena hiding in our plain sight. We all know that moment when we are washing our dishes and water just explodes all over our shirt, or when it's raining and our helmets or our windshield creates a messy blur. We all have seen it, but have you ever stopped and wondered why water behaves differently on different surfaces? There is an incredible, complex battle happening between forces that we can't see, and today I'm going to blow your mind.
First, let's define what we mean by splashing. When a droplet hits a surface, one of three things can happen. 1. It spreads smoothly across the surface. 2. It bounces back like a rubber ball. 3. It explodes into dozens of tiny droplets. And that's splashing.
Now, you might think it's just about how hard the water hits the surface, but that's only just a part of the story. The real answer involves something called Weber number.
The Weber number basically compares the droplet's momentum to its surface tension. Oversimplifying surface tension, it is the water's stickiness to itself. Higher the Weber number, higher the chances of splashing. But here's where it gets crazy. The surface itself can completely change this equation. Alright, prepare for your mind to be blown. You might think water instantly touches a surface, right? Wrong. In the milliseconds before impact, an invisible cushion of air forms beneath the droplet. An air layer so thin it's only about 1 micron thick. To truly grasp that, consider this. A human hair is roughly 75 microns thick, yet this unseen cushion is incredibly powerful. As the droplet approaches, the droplet actually deforms into a dimple shape because of this compressed air. Sometimes the droplet just bounces right off the air cushion without even touching the surface. And here's the fun part. Scientists have proven that if you reduce air pressure, splashing decreases dramatically. In a partial vacuum, droplets that would normally create huge splashes just don't. The air isn't dense enough to create that cushioning effect. This means that technically, water splashes differently on Mars than on Earth just because of the thinner atmosphere. Now let's talk what happens when the water actually makes contact. At molecular level, there's a constant tug of war happening between two types of forces. Coercive force is the force where water molecules want to stick to each other. This is what creates surface tension and forms water droplets. Adhesive force is the force where water molecules want to stick to the surface. The winner of this molecular battle determines whether water spreads out or beads up. Scientists measure this with something called contact angle. Less than 90 degrees means the surface wins and water spreads out. This is hydrophobic or water loving. More than 90 degrees means water wins. It forms beads and is more likely to splash. This is hydrophobic or water fearing. But wait, it gets even crazier. Some surfaces are so hydrophobic they are called superhydrophobic and contact angles are over 150 degrees. On these surfaces, water droplets are almost perfectly spherical. The lotus leaf is the classic example.
Putting these aside, rougher surfaces should create more splashing, right? Not really. High surface roughness can actually do both. Let me explain.
High roughness makes hydrophilic surfaces more hydrophilic, increasing splashing by disrupting the thin sheet of liquid that spreads out on impact. These tiny bumps create instabilities that cause the liquid sheet to break apart. Meanwhile, hydrophobic surfaces become even more hydrophobic, and with specific patterns, they can actually suppress splashing completely. This is the principle behind self-cleaning surfaces. This happens because the right kind of roughness gives the compressed air layer somewhere to escape instead of building up pressure and causing explosive splashing. The air can flow through channels in the surface. Engineers are now designing surfaces with specific pillar heights and spacing to control splashing exactly the way they want.
Now let's talk about temperature. Temperature adds another whole layer of complexity. You might have probably seen water droplets dancing off a hot pan. That is called Leidenfrost effect.
When the surface is hot enough, the bottom of water droplet instantly vaporizes, creating a cushion of steam that the droplet floats on. It's like the air cushion we talked about earlier, but made of water vapor. In this state, the droplet can't actually touch the hot surface, so it does not splash. It just glides around like it's hovering.
But at intermediate temperatures, not hot enough for the water to boil and not hot enough for the Leidenfrost effect to take place. At this point, we get the most violent splashing of all. When the droplet hits the surface at this temperature, it immediately starts to boil, and the expanding steam literally explodes the droplet apart. So, why does any of this matter at all? Well, understanding splashing has a huge real world implications.
Inkjet printers need to control droplet behavior precisely. Too much splashing and your prints are blurry. In agriculture, farmers want pesticides and fertilizers to stick to leaves, not splash off and waste the product. Engineers are designing self-cleaning surfaces that use controlled splashing to wash themselves. When water hits these surfaces just right, it bounces off taking dirt with it. Meanwhile, car manufacturers are developing windshield coatings that minimize water splashing for better visibility in rain.
Let's talk about energy, because that's really what splashing is all about. When a droplet hits a surface, it has some kinetic energy. This energy has to go somewhere, so it can either be converted into spreading energy or surface energy, or it can be dissipated into heat through friction. When the surface can efficiently absorb or dissipate this energy via spreading or friction, you get a smooth wetting. However, if this energy can't be efficiently absorbed, then it gets released violently as splashing. This is why even viscosity matters. The internal friction between the particles helps to dissipate this energy and hence reducing splashing. It's counterintuitive. We would think that thicker particles or thicker surfaces would generate more splashing, but these are very good at dissipating their own impact energies. Honey is the best example for this. So, the next time when you see water hit a surface, remember you are actually observing one of the most complex physics phenomena in nature. There is an invisible air cushion, there are molecules battling for dominance, there is compressed gas trying to escape, and there are energy transformations.
Scientists have been studying this for centuries now, and we are still discovering new mechanisms. And that's the beauty of physics. Even the simplest looking things can hide incredible complexity.
If you're as fascinated by the hidden science in our everyday world as I am, then don't miss out. Make sure you subscribe and hit that notification bell so that you don't miss out my next videos. See ya!